So remember that we are having a quiz on Friday. It would talk about related rates.
Hey, Mr. Train, I'm here.
Okay, what's that?
Ian.
Ian, okay, thank you. And so linear approximation. So prepare that. Then we have 2 questions. And we'll do it in 20 minutes. Okay. And the test 2 will be similar to the quiz. Okay. Today we will talk about section 4.4. 4.1, I'm sorry, about maximum and minimum. So tomorrow, if you have any questions about related rates or linear approximation, I'm pleased to answer some quick questions. And on Friday, we will correct the quiz too, so that you can. For now, let us continue. Thank you, Ethan. Okay, let us continue. So the maximum and minimum's value is very important in real life. So, for example, how to spend less time studying math, still got high score. Right? Spend less time, but understand it more. It's really hard, right? And or sell as many products as we want in a short amount of time, whatever. There are so many important problems in real life that we want to study. So suppose we are given a function f, which is defined on this interval. From 1 to 5, and here it is 2, it is 1. Okay. This is 4. This is 3. And so this function is defined on the domain from 1 to 5. Can anybody tell me what is the maximum value of the function f here? The highest value of the function f?
3.
Perfect, thank you. This point, right? And the lowest value of f? 1. Very good. So, thank you. So we call it here because it is the highest value of the function f over the whole domain, right? We call it the absolute value maximum. F at 2 here, we call it absolute maximum value of the function f on the domain from 1 to 5, right? It's easy to see. And the function value at 4 is the lowest value, so we call it absolute minimum. Of the function f on the domain from 1 to 5. Just some concept definition, right? So, mark it here. Okay, very good. So let us define something. First, let C be a number. I think it is better to type it here. C be a number in the domain D of a function f and we call FC is a absolute value and maximum value of f on D if f of C is greater or equal to f of x for all x in D. Okay. Similarly, we call it absolute minimum if f of C is smaller or equal to fx for all x in D. Okay, very important that it is all over the domain. Okay. Sometimes we call them the global maximum or global minimum. So this one, absolute maximum, or we can call it or the minimum, we call it global minimum. Okay. And the maximum and minimum values of f, we call it the extreme values. So some new definition, right? There's nothing very special yet, but we need to remember these things. Okay. Now, these are definition, right? Let us take a look at the graph here. So if the graph of a function f is shown as like this one, right? Okay. This is the function f of x here. From definition, what is the local global minimum and global maximum? Look at this, the lowest. It is defined in this interval, right? Let me just write it down. Let us, okay, if this is 1, 3, 5, and here let us call it -3. So suppose this is defined from -3 to 5, and this is the function f. So what is the lowest point of the function f? Perfect. F at -3, this point, right? Very good. So it is the lowest point, and it's smaller than any f of x from the domain from -3 to 5. So this is the global minimum, right? This point. And what is the highest point?
+3.
Yes, very good. Who was that?
Michael.
Thank you, Michael. So that is global maximum. And how about this point at, let us call it right here, at 0. So from the interval from -3 to 1, what is the maximum value of this function from this interval? At 0, right? So, but it is the maximum in this local area near this position. So we call it local maximum of the function f in the intervals from on the interval from -3 to 1. Okay. How about this special point right here when f is equal to f of 1? It's smaller
The
than,
local minimum.
yes, local minimum. Thank you. Who was that?
Ashley.
Ashley, thank you. Okay, local minimum at x is equal to 1. So now, what do you think about the tangent line of these points? Yeah, it is. The tangent line is horizontal, or the slope of that is 0. At local maximum here, oh, sorry. At local maximum here, and global maximum here, right? But the derivative of this at 1 is very special. With this graph, the limit, if it approach from the right side of 1, the limit of this, it means the slope will be a positive number, right? Look at this. It should be somehow like this, right? But if it approach from the left, it will be a negative because it's decreasing, right? So the f prime, the slope of this, the derivative of this is not defined. So let us skip it for now, but that is some notice. And let us put a remark right here at this point. Okay. Now, we have some definition. Because it is the maximum near the neighborhood here, or locally, we have a definition about the number f of c is a local maximum. Value of the function f if f of c is greater or equal to f of x when x is near the point C. And similarly, we have the local minimum of f if f of c is smaller or equal to f of x near c. So remember, this is near c, okay? Locally near the point. So that is why we call it local maximum and local minimum. We haven't studied that much, right? Just some definition. Let us take a look at this example. So if we are given a function f of x is this function, and let us say it continues for very small x and very large x. So what, let me point down. Let us call it A, B, and C. At A, what is it? Yes.
Local minimum.
Thank you. It is a local minimum. Who was that? Thank you, Justini. How about at B?
Global max.
Maximum.
Yes, it is a local maximum. This is a local minimum. And near the neighborhood of this, which is near A, right? And local max here, it is local max near B. And at the point C here, is it a local minimums or maximum?
Absolute minimum.
Local minimum is the lowest point near this area, right? Let's see. So we see that at all these positions, the slope of this is zero, right? Or the tangent lines of these points is horizontal. Okay. Some concepts. Now, let us play with a specific example. So let us consider the function f of x, which is x squared here, right? So the graph of this, we can plot it in the coordinate. It will go through at x is equal to 0, f is 0, at x is equal to 1, then f of 1 is 1, and so on. So the graph of this is like this, okay? So now, according to the graph, we know that, okay, at 0 is a, what is it?
Local minimum.
Yes, it is a local minimum. And the slope of that is 0, right? Or the slope, the tangent line is horizontal. Let us compute the first derivative of this function at that point, right? So what is the derivative of f of x here in this case? Thank you. So we see that the derivative of any point will be 2x. Therefore, what is it at x is equal to 0?
0.
Yes. At 0, the f prime will be 2 times 0, which is 0. Very good. So it is interesting, right? It confirmed that, okay, at f prime at 0 is 0, makes sense with the graph here. Okay. Who was responding to me on Zoom? Who was that?
That was me.
Michael?
Vikram.
Vikram, thank you. Okay, now we have a theorem, the extreme value theorem. Interesting. How can I pull it out? Okay. So if the function f is continuous on a closed interval from A to B, then f attain an absolute maximums value, fc, and an absolute minimum. At the point D, at some number C and D in the closed interval AB. So it is very interesting. Now let us take a look at this. Bless you. So suppose the function f is like this. Oops. Okay. Now, and it is defined from the interval from A to B, and let us call it 3 here, 6, 9, 12, right here. This function is continuous, right? We can draw it without taking our hand up. We can draw it continuously. So, and we know that the domain is from 3 to 12. And the extreme value theorems tell us that, okay, it attains a minimums, absolute minimums and absolute maximum, which is, what is it in this case?
3.
Yes, at the maximum value is at f of 3, right? This is the maximum value. And what is the, oh, this is minimum, I'm sorry. And what is the maximum value of the function?
12.
Yes, f of 12. So 12 is the position where the function f reach its maximum and minimum. But the maximum and minimum values of f is f of 3 and f of 12, okay? Just some concepts. And here, how about these points? What are they?
Your local
Local max and minimums.
Thank you. It is local max and local minimums. Who was that? Sorry.
Ashley.
Ashley, thank you. So those are local maximums and local minimums. Very good. And okay, this is global max and global okay, very good. How about this one? It is a little tricky. Let me see. Okay, now this graph is a little tricky. Okay. That is a very interesting question, Ashley. But no, hold it for now. We will take a look at these and we will talk about this a little later. Very good. Now, you see that, so suppose this is 3 and this is 7. This is 13, right? So what is the domain of this function f? Yeah, from 3 to 13, right? It is defined on this interval. Very good. So from this intervals, what is the minimum value of the function f? F of 13, so be careful, right? That is the lowest value of the function f. Okay, it is a global minimum. If it is a global minimum, it is also a local minimum. So, right, but if a point is a local minimum, it may not be a global minimum, okay? So now, what is the maximum value of the function? At 7? Approach 7? So we see that from the definition. The definition on top here. Sorry, somewhere right here. The absolute maximum value is f of c at that point. It means that f of c should be defined at that point, right? However, the function we have here, f at 7, what is it? It is not defined, right? Yeah, there's a jump right here. It is not continuous, right? F at 7 is not defined, so F7 is not a local global maximum. And in this example, there's no maximum global or, I'm sorry, F at 7 is defined right here, I'm sorry. It is at this point. Sorry about this. It is right here. Sorry, it is defined, right? But for any values which is larger, greater than any value of x which is greater than 7, it will be around this area, right? For any values which is smaller than 7, f of that will be here on the left, right? So it means that f of 7 sometimes is larger than something and smaller than something. So it is not defined here. F of 7 is not a and in fact, the function f here does not have a maximum. Okay, it's a little tricky. but it does not contradict the the extreme value theorem. Because in the theorem, we say that a function should be continuous, right? But this function is not continuous. There's a jump here in the middle of it at 7. So, okay. Now, how to find an extremus for a function f? That is a very good question. And yeah, that is a question. And Ashley asked us a very interesting question. She asked whether the slope is always 0. So let us talk about this. Okay, now take a look at this example. The function f of x is x cubed. Okay, look at this. The graph of this, we can draw it easily. You can plot it by finding some values, and it should be like this. At 0, it is 0 right here. So now let us find the first derivative of this function, right? What is it? What is the derivative of f of x?
3x squared.
Thank you. And we see that at 0, what is the slope of this?
0.
Yes. So what is the tangent line at 0 of this function? Right, the tangent line equation is this one, right? Or we see that it will be y, this is 0, f prime is 0. It means y is equal to 0. So the tangent line is this line. It cut the graph at only one point, but this point at x is equal to 0, f of 0 is not a maximum or a minimum, right? Because we see that f of 0 is equal to 0. It's smaller than any value function f of x if x is larger than 0, right? And f of 0 is always larger than f of x for any x smaller than 0. It is not a local maximum or minimum. Okay? But the slope of this is 0. Right? It is very interesting. So be careful. So it means that to answer the question of Ashley, we see that when the slope is 0, it may not be a maximum or a minimum. And we have a very important theorem, Fermat theorem. Fermat says that, okay, if f has a local maximum, or local minimums, at C, and if f prime at C exist, then f prime at c is equal to 0. If the derivative at that point exists, it should be 0. This theorem, okay? Now, let us take a look at the example here and see. If the function f of x is absolute value of x, then specifically, what does it mean? Yes, x, if x is positive, and negative x, if x is negative. So, and we can draw a graph of this function, right? Oops. Okay, this is the x coordinate. This is the y coordinate. If x is positive, then y equal to x. And if x is negative, then y is equal to negative x. This is the function y equal absolute value of x. Okay? So what is f at 0? I'm sorry? Yes. F at 0 is 0 right here at this point, right? So we see that according to the graph, is it a maximum or a minimum?
Minimum.
Yeah, it is a minimum, yes. It is local minimum and it is also a global minimum. Because for any value of x, put it into the function, it is always larger than or equal to this. Very good. So, but look at this. What is the derivative of this function at 0? Very good, Yasini. It does not exist. We've done this many times, right? The derivative of this does not exist. Okay? Why? Because let us take the limit. When h approaches 0 plus, at 0 plus h here, right? Minus f at 0 over h here, right? Let us write it x here, it's better. F of x, better expression. Okay, what is it? It means that x approaches 0 from the right-hand side, right? It means that x is positive. If x is positive, then f of x will be? Yes, f of x is x. And what is f at 0? 0. And divided by x, right? So it means that this guy is the limit of a constant 1. Right? The limit of a constant is a constant, that constant. And similarly, if the function, if the limit x approaches from the left side of 0, what does it become? Very good. Thank you, Harrison. It would be the limit from where x approaches the left side of 0 of negative x minus 0 divided by x, which is the limit of negative 1 when x approaches 0 from the left-hand side. The same story. The limit of a constant, negative 1, will be that constant, negative 1. So the limit from the left and the right are different. So the derivative does not exist at 0 here, right? That is why we have this. From these two, we say that, okay? So here, it is very interesting that the derivative is not defined here at 0, but it is still a minimum, right? Very tricky, okay? And let us take a quick notes here. So if f prime at c is equal to c equal to 0, there need not be a maximum or a minimum, right? And from this right here example, there may be an extreme value even when f prime at that point does not exist. It is very interesting. So I think we can continue tomorrow. So remember, tomorrow we will continue doing this, but I will answer any questions you have about related rates and linear approximation of a function. Okay? And we will take the quiz in class on Friday about these two. Okay, have a good one. And we have an office hour this afternoon from 3:30 to 4:20. You can come there to ask me.